Okay, I will start with my presentation. I will present my project. It's about implementing the SP3 approximation for radiation heat transfer in open form. Here I show you some agenda. We will go through about this. First, I start with a little bit introduction. Then some about the spherical harmonics approximation, the PN models. Then P1 and SP3 approximation. Then I will talk about the implementation in open form and the results in the case study. So finally with the conclusions and the future work. Oh, sorry. I don't know what happened. I'm so sorry. I don't know. I'm really okay. Okay, sorry. Here I start with the radiation. It is important to know what is the radiation. So that it's important to talk about the radiation because all the time we are constantly exposed to the radiation, mostly from the natural source like the sun. But the question is, what is radiation? So radiation is a type of a heat transfer that occurs through electromagnetic waves. It's a product of the emission by the different source due to its temperature. Unlike conduction and convection, radiation doesn't need a physical medium to propagate, like a sunlight reaching the Earth. So radiation covers a wide range of the wavelengths, from infrared waves to associated with the heat, to visible light and ultraviolet rays. So radiation have a lot of application, but one of the most important is in the fire safety. Since in a fire, this heat can reach nearby objects, causing serious harm to the people with burns or causing the ignition of flammable materials. In enclosed space, the radiation can significantly accelerate the spread of the fire. This happens because nearby objects absorb heat and reach their ignition point more quickly. Currently, there are applications that use hydrogen as an energy source. And one of the most important challenges is the safety when is present a scenario with the hydrogen jet flames. This is because hydrogen flames emit less visible radiation than the hydrocarbon flames, which makes them difficult to detect, increasing the risk, of course, of accidents and complicating emergency response. So the question is, three questions really. Radiation is dangerous? How much is intensity? It is possible to measure? Well, thermal radiation becomes dangerous when the distance to the heat source is short, due to the intensity of the radiation increases significantly when the object is closer to the source. The intensity of the radiation depends on the temperature of the flames and the distance between the source and the receiving objects. For example, we can see the image when how radiation waves reach a person's hands without causing harms. But it's possible to measure. Here, I show you that, of course, it is possible. We have two different options here. One of them is with calculations, using different mathematical models to calculate and study what is the behavior and simulate the behavior of this radiation. But also it can be determined experimentally using, for example, radiometers or spectroradiometers. Here I show you some numerical solution that can be used to calculate the radiation. One of them is the discrete originites method, DOM, Monte Carlo, Roseland mean approximation. Each one have a principal thing that have, but I focus in the one of them. This is the spherical harmonic approximations, all called PN models. This model simplifies a radiative transfer equation into solvable partial differential equations. It's where high-order approximations improve accuracy in anisotropic or optical thin media. This order of approximation is defined with this letter N. I talk a little bit more in the next slides. So here I show what it's the different models that the OpenFOAM used to solve the radiations. And I underline the P1 model because this model, it's part of the PN approximation and used the spherical harmonics. So here I present the radiation model in OpenFOAM that is the P1 model and the model that I will implement it. The P1 model is the simplest form of the spherical harmonic method. It is suitable for problems where the properties of the medium are homogeneous and complex angular detail are not required. Its weakness is accuracy in capturing angular variations, the direction in which radiation is propagated. The SP3 model extends the P1 method by including high-order terms. This model improves accuracy in capturing angular variation of radiation. This model is best suited for problems where anisotropic properties or angular variation of radiation have a significant impact on the results. Well, specifically, what are the spherical harmonics about and how are they useful to solve the radiation equation? Here I show you this equation that show the terms of the spherical harmonics and a figure that shows the different force that depends the two I can call the two different letters, but we can call specifically the name is the quantum numbers that shows that the behavior of this different, the angular momentum and the or it depends of the each angular. So spherical harmonics are mathematical function that used to describe the angular variation of a defined function on the surface of a sphere. That's the example. They are commonly employed in physics, especially in problems that involve angle-dependent fields or distribution, such as wave equation solution, or in this case, radiation model. L, it's a number that represents the number of the angular nodes in the function. If L increases, the function showed greater complexity in their angular structure. M depends of the L number, and this is the function that show varies along the azimuthal axis. I mean, this shows the rotation around the vertical axis. Here, we can see that the first equation, it's the spherical harmonics. But the spherical harmonics depends of the associated Legendre polynomials, and of course, depends of the two different numbers, the L and M that I just explained. In radiation models, such as P1 or SP3, radiative intensity can be expanded to capture angular variation in radiation. Now, the radiation equation depends on the several parameters, so that is important that I can show what it's these key parameters on this equation to calculate and use the spherical harmonics. So here I have the important, this is the spectral radiative intensity. We have coefficients, the absorption coefficient. This is the absorption coefficient. This is the extinction coefficient. And this is the spectral scattering coefficient. Here we can see in this graph that these waves represent the intensity from the source to the object, in this case, the hand. And here it's the different behavior when transmitted the energy or absorbed or scattered in this case. Previously, I explained the physical characteristics. Now, these characteristics are determined by solid angle that represents a portion of three-dimensional space from a reference point. The next is the unit vector in a given direction. This we can see here. This defines the direction in which radiation propagates. The other is the scattering phase function. This describes how radiation is scattered from an original direction is redistributed to a new direction. Here we have two angles. This is the polar angle. The polar angle is an angle between the unit vector and the axis normal to the plane. In this case, is the z direction. The other is the azimuthal angle that defines the rotation of the direction vector. Well, once we have defined what spherical harmonics are and the parameters of the equation of radiation, we will now apply it in two different models. This is the P1, the first one model. In the P1 model, the radiation, the radiative intensity is truncated beyond L equal 1. And below that, it's the M, it's the number, the M, it's between the minus L to plus L. So in this case, if the L is equal 1, the possible values that M that can be used, it's the plus 1, 0, and minus 1. So if we use this in the spherical harmonic, that it's the equation that we obtained. In this equation, the first term with L, it's equal 0. It's called the zero moment, which describes a uniform intensity, while the remaining terms, in this case, the three terms, depends on the angles, model the direction variation, and it's called the first moment. This makes the model efficient, but less accurate in case we have anisotropic. Here we have two different definitions to the incident radiation and radiative heat flux. If we solve using this equation and some steps, mathematical steps, we can obtain the intensity in this form, where the radiative intensity, it's a combination of incident radiation and radiative heat flux. After, of course, a file detail that if you go on the course, you can see in my report, the main equation of the P1 approximation are obtained, and this equation have this form. In this model, we can use a single elliptic second order partial differential equation for the incident radiation. It's this second. And in this case, P1 approximation turns the entire radiative problem into a more easy model. We can call solving only incident radiation and radiative heat flux. This is the incident radiation and radiative heat flux. So here we have a new term. This term is the albedo that depends of the two, this coefficient that we called before, this the scattering and the extinction coefficient. Here we have more equations, a little bit more, but this is important to show because all these equations are used in the model, and it is important to understand a little bit to why it's the difference with the SP3 approximation. So in the P1 approximation, the radiative heat flux, Q, depends on how the incident radiation changes with the medium, within the medium, sorry. This is adjusted for factors such as albedo that I called before, this, which measure how much of the radiation is scattered rather than absorbed. Here we have the Marshak boundary condition for this model that describe how radiation interacts with the surface. Some is reflected, absorbed, and the rest of transmitted. Here we have the graphs, and we can see what is the behavior of the radiation that incident with the surface and the possible behavior of the wavelengths when if it's reflected, maybe in the absorbed the surface and possible transmitted. So following the same definition where the letter N represents the order of the approximation, here SP3, it's SP3 approximation. The radiative intensity, it's approximated, but in this case, we are trunk the L, it's equal to 3. But if we remember the number M that depends the letter L, the all numbers M is between minus L to plus L. So in this case, we have some different terms that depends the this is the momentum 3, 2, 1, and 0. But this is the final equation that we obtain in this SP3 approximation. The question is, it's correct because we only have two. Okay, so in order to answer whether it is correct or not, let's clarify what the definition of the SP3 is. Where it is come. 3, of course, it's a part of the simplified PN approximations. I mean, reduce the complexity of the PN equations. And this, of course, consider all ordered terms are treated as a vector with a divergency operator, I'm sorry. And even ordered terms remain scalar with gradients. Here I show you the radiative intensity could be decomposed into a sum of a coefficient that depends on the optical thickness multiplied by the Legendre polynomials. By substituting this expansion with the L, it's equal 0 and depends to the until arrive to the L equal 3. And we are substituting and taking advantage of the orthogonal property of the Legendre polynomials. A system, a couple of equations is obtained. These equations describes the coefficient of the intensity expression. Here we have, this is the equation that I used to obtain this expression. Since we say that the simplified PN model reduces the complexity of the PN equations, the SP3 models reduce the complexity of the P3 approximation. So in the P3 models, it allows to capture second and third order of the details or anisotropies in radiation, offering greater precision than a simple approximation such as P1 approximation, the last model. But in highly symmetric systems, such as isothermal media, both orders like L equal 3 or L equal 1 do not contribute due to the cancellation of angular integrals, making the additional complexity and not bring significant improvements. The SP3 models was development to overcome this limitation by simplifying the equation of the P3 models, while maintaining accuracy in the results. In the SP3, eliminates cross terms and complex derivative presence in the P3 models, significantly reducing the computational cost. Unlike the P1, the SP3 approximation can represent more accurate directional variation, such as second-order anisotropies, making it better suitable for optical thick media. Of course, the solve these equations and all the details, if you can see my report, of course, it's a big solving. So here I show you the final equations that obtained in the SP3 models, where given all the restriction, limitation, and simplification that we have analyzed, the SP3 models confirms that focusing only in a terms with L is equal 0 and L is equal 2 to validate the approximation. Here we have two elliptic partial differential equations, which are coupled. So in the first equation, it describes the zero moment is this J0, which represents isotropic or uniform radiation in all directions. And here we have the other equation, the second equation, that depends on the J2. And this is the second order momentum, which incorporates the most important angular variations to capture quadratic anisotropies. Both equations combine effects such as absorption, scattering, radiative source, and must be solved simultaneously due to their independence. We have here the incident radiation and heat flux that depends on these again moments. Finally, we have here the Marshak boundary condition. To solve this, again, we need to consider all the limitation and the symmetry of the using polynomial and all the functions. And in here, specify this boundary condition specify how radiation interacts with system surface, describing, of course, the process of the absorption, reflection in the surface. This condition, of course, ensure a precise energy balance of the edge of the medium. Well, this is the first part, the part of the theory. So now we'll show you the implementation of the SP3 model. Here, I'm sorry, here, this is the directory structure. The radiation models in OpenFOAM is part of the thermophysical model. In the directory, in the radiation models, where there is the P1 approximation, it's create another folder, the SP3, with have two different files, which are the ones that implemented the equations of the SP3 models. Here, SP3 Marshak radiation, it's another file to handling the boundary condition for the model. Okay, in the SP3 file, the constructor of the SP3 class initialize the variables for the model to the models. For example, the scalar field, but we need to initialize this. This is the second order of the moment. These are the coefficient of the absorption and the diffusion coefficient. And each variable is defined using the IObjects class, because in this case it's necessary to specify this behavior, such as whether it should be read from an initial file or whether it will be written automatically during the simulation. Here, I continue to implementing this. In the calculate function, the absorption and emission coefficient are retrieved first. This means that the program access to the value or property that are already defined. So here we define the absorption coefficient, diffusion for each mode. Then we can see here the diffusion coefficient for the moment are occurred considering all the different coefficient. And here we can see that we have a letter that this is A0. A0, it's called a stabilization term. These coefficients are fundamental for modeling radiative propagation, and it's to ensure that the division it's positive, that it's possible to solve. Then we need to put the equations to solve the problem. That if we remember that we need to use two different equations that depends one of the other. So this case, the equation for the zero moment, which represents the isotropic moment, is solved in this calculate. Here it used this function for the diffusion term, and the next is the FBM for the absorption terms. This equation, of course, includes all the terms and an explicit coupled terms with the second equation. Here we have the implementation of the second equation. This is the second equation of the model, and the coupling term. This equation model how quadratic anisotropies behave in the middle. The coupled term, this part, it's important to put because it's explicitly calculated as an additional term called coupling, which used the gradient of incident radiation. This term is essential to capture the interaction between both moments. If we continue in this part, the radiation flux is calculated at the domain boundary using gradients of G. This is for these boundary fields for the radiative flux, and this is the boundary for the gradients G, the first moment, the zero moment, sorry, and this is the second order moment. This is the boundaries to call to the gamma. This is the coefficient, and this entires over the boundary patch, differentiation between coupled and uncoupled patches, because it's important to remember that we need to solve in a coupled time. Here, this is the implementation, but in the boundary condition. During the simulation setup, the values required for the diffusivity associated with the zero and the second moment. This is the zero and the second moment. And this is required directly from the file systems using this function, lookup patch file method. This allows specifically boundary condition to be automatically initialized from the parameters defining the input configuration. Here, I'll show you another part when I use the value fraction. The calculation and updating of the boundary values, the model, it's here in detail. When calculate the effective emissivity factor, when calculate the value fraction for the SP3, and of course, update boundary values for the second order moment. So here it's important to see that there is a factor, but what is this factor? The factor, this 0.5, is used to correctly normalize and scale the second moment. Is second moment J2, where is here? This is the second moment, based on the property of orthogonality and normalization of the Legendre polynomials. This factor ensures physical and mathematical consistency between the two moments, the zero moments and the second order moments, and of course in the boundary condition. This part was the implementation. So I'll show you the case study that I used to compare the results in both in the both models. I used the small pool fire. This is the line where is the part of the when you can find the small pool fires in the fire foam. In this case is based on the simulation of the radiative heat transfer and transfer distribution in a fire with methane as a fuel. The principal objective is to analyze how radiation models predict a heat release rate and incident radiative heat flux. In this model, it's important mention that the methane is used, but as a gaseous fuel that represent the radiative effects in the fire environment. So commonly is in the pool fire, you can use a liquid fuel, but in this case, the methane shows it's used as a gaseous fuel. This is a physical and numerical models that I put in the model. The turbulence used is the large edit simulation. The combustion, it's a dirty dissipation model. In the radiative heat transfer, I choose the two models, and I run and compare the results. In the emission and absorption, I use the constant absorption emission, with case depends of the coefficient. In the SP3 models approximation, it's necessary to put which is the each coefficient in the models to run the case. We don't consider the formation, so that it's the physical and the numerical models at first. Then, in the case, it's necessary to make a few change or to run before. So in the first part, in the constant directory, in the file radiation properties, it's necessary to put what model I will use. In this case, I will use the SP3, the new model implemented. And when in the implementation, I put that all these coefficients will be read from the data in the case. So here it's, I put which are the SP3 coefficients. This coefficient depends, of course, the scenario and the model that used to solve. The other thing that it's necessary to change is in system directory, in the file FV solutions. It's important to put the new moment, because we use the two models and two moments, the zero and the second order moment, that all the two moments is coupled, so they need to solve at the same time. So here we put with the same characteristics, the G and J2. They use the same solver, they use the same tolerance, and that is to ensure the efficient convergence in both radiation and radiation models. The other change that it's necessary to do is in the system directory, in the FV scans, it's necessary to add what is the moment, the both moment. In this case, it's the moment, the first and the second moment, to ensure, in this case, accuracy in the calculations of the gradients and the divergences. Another thing that it's necessary to do is create a new file to initialize the second order moment. This is part of the folder 0. This is the structure similar to the first moment that the all models radiation have, is the G, the incident radiation. But the difference in this case, it's necessary to use the boundary condition. This is the new boundary condition that I use. This is the SP3 Marshak radiation. Again, this is important because we need to ensure the correct interactions of radiative heat flux and edge of the domain. Okay, this is the first part that it's necessary to put. And then if the principal main is to calculate the heat release rate, the temperature, the incident radiation. So to obtain this data, it's necessary to make a sum function. This function is made in the control dict. This is function for obtain the heat release rate. This is the function to obtain the measure of the temperature in different positions of the flame. If the flames occurred in one area, we need to measure what is the temperature in different distance to see what the radiation, what is the temperature increase and what is the relation with the radiation. But here, I would like to mention one important thing. It's a comment and a question from Said, and thank you for the comment. And it's the question, it was why I use the thermocouple proofs and why I don't use the proofs. This is the other function. So in my case, I choose this function, the thermocouple proofs, because this function includes specific features for simulating physical thermocouples, while proofs, the function proofs, simply records file value at defined points without considering the physical property of the sensor. In my goal, it's to get closer to reality so that in a future work, of course, it can be compared with experimental data. This I'll show you this where is the located of these proofs, and this is the other different function to obtain the incident, the method of the incident radiation. Here it's the one of the results. It's obtaining along to the central line, and that we can see what it's the different behavior that the colors, because if the colors represent the intensity of the radiation of each point of the domain, of course, if the color is red, that this indicates it's a higher intensity of the radiation. Here is it's possible to see what is the different the models. In the first part of the presentation, I said that the P1 model, P1 approximation, don't consider the all directions, only consider this model is isotropic. But the SP3 models consider the second order moment that study that consider what happened the direction with the different radiation. What happened if the distance? What happened if how much radiation reach of each object? So in this case, we see what it's the position of the three thermocouples. So in the measures that in this case it's showed it's in the third thermocouples TC2, and in the line the blue curve correspond to the P1 models, which overestimated the temperature in regions far from the source. That is the region, and it doesn't capture anisotropic accurately. The red line represents the SP3 models, which shows a more modern prediction due to its ability to consider the second order anisotropic. So it's possible to see that the radiation, it's not necessary to reach all radiation in one point. So it depends the direction of the disperse or scatter this radiation. Here I can show you the other two results. These results show the incident radiance measured in the 2 points. I want to return this is I can continue with these points. So it's important to see again that the blue it's the line that show the behavior of the P1 approximation, and the red, of course, it's the SP3 models. That this is reasonable to see the behavior, because if there is if it exists the dispersion, if all radiation is emitting or all the reaction is, it's important to see. Oh, maybe the question will be where is the radiation that is dispersed? If not reach at one point, where is that radiation? So this is one that I comment that this is a possible future work to see what happened with the radiation, to see what happened with this. And of course, it's important to see that here the total time analyzed, it's very, very short. So we don't predict the real behavior of the model, but it's only because of the cost of computational and the time that I need to, of course, run. This is another future work that I propose. So I think it's all. This is all I can present, and this is some conclusions and the future works. So in the conclusion, it's that of course the SP3 model approximation shows what it's the different consider more, of course, the anisotropic, not all, of course, not all, because it's necessary to refine the model, to refine a little bit more. But in principle, it's a good direction. It's almost close to reality, of course, we can say. In the future works, I can show you that we can consider the turbulence model and compare what happened. The angular validation, it's that I told before. This we can add measures and various angles and distance to validate this model. And of course, we'll see what happened. Where is the radiation? That it's not lost, of course, but where is? And the next, it's of course advanced boundary conditions to incorporate another reflective in the semi-transparent, because you see, in this is a solid, what is composed if the thing increase, if the thickness depends of the thickness, of course. Okay, that is all. Thank you.